So we've talked about the period of a simple harmonic oscillator, and we also talked about a little earlier, if we have a pendulum's displacement being less than about 15 degrees, we can also treat it as a simple harmonic oscillator. It's a little special. We can actually get a formula for the period of the pendulum. So we're going to look at that. So again, recall that the restoring force on a pendulum is going to be this negative Fg times sine of the angle. And we're going to use a little trick. This is also where that whole 15-degree thing comes in. Now, if we have a really small displacement from equilibrium, this is the distance that we've actually displaced, like along this curve here. But what we're going to find is if we keep that angle small, we can, instead of using this curve, we could kind of use this horizontal distance from the equilibrium position to the pendulum bob. We're going to find that for small angles, this distance along this curve and that horizontal distance there, they're quite small. There's not really a large difference. So we're going to make some approximations. Does this affect the exactness of the answer? Yes. Do we still get some good physics out of it and get some great understanding? Absolutely. Well, we can see here that if we know this side, this little displacement x, and we have this angle and this length, well, we know that sine of this angle is going to be that small displacement horizontally divided by the length of the pendulum. Well, good news. In the equation for the restoring force, we have a sine. We also have sine here. So what we're going to do is, instead of having negative Fg times sine of theta, we're going to have negative Fg times x over L. So this is going to, again, work if we keep that angle really small. So we're going to keep theta to be just under 15 degrees. Now, we also know in a mass spring system or any system that is undergoing simple harmonic motion, it's going to obey Hooke's law. So that restoring force, we can write that as negative kx. And then we have this negative, instead of Fg, we'll write mg, and then we have this x over L. So somebody might ask, well, why are we using kx for a pendulum? It's not a spring. So what we're trying to do is we're trying to find the equivalent of the elastic constant or this spring constant for a pendulum. It's not quite spring constant. We're just going to use this to kind of help us get a formula for the period. So we don't really care about the negatives. They will cancel. Though that little small displacement from equilibrium, that also goes away. So what we're left with is this k equals mg over L. So we're going to kind of think of this as the spring constant of the pendulum. Doesn't make a lot of sense. Stick with me on that one. Now, for anything that's obeying simple harmonic motion, we know that t is equal to 2 pi times the square root of m over k. Well, for a pendulum, we know that k is just going to be this mg over L. So that's what we're going to dump in here. So we have t is equal to 2 pi square root of mass, and then we're going to divide this by mg over L. Now, the masses are going to cancel out. Under this square root, though, I'm going to have 1 divided by g divided by L. That's ugly. Fraction within a fraction, we don't want that. This is the same thing as just saying, well, we know that 1 divided by a fraction is the same as saying 1 times the inverse of this. So instead of L over g over L, we're going to have L over G. What that means is the square root of 1 over G over L is just the same thing as saying the square root of L over G. So we're going to get 2 pi times the square root of L divided by G. So this brings us to the fruits of our mathematical labor. So we are going to get t equals 2 pi times the square root of L over G. This is the formula to determine the period of a pendulum. You need to know the length of the pendulum. You need to know the acceleration due to gravity for that pendulum. Now, this is a special case. This is only for pendulums. If you don't know anything, if you are not using a pendulum, you need to go to this equation. This is the general equation for simple harmonic oscillators. This is a special case. So t is going to be the period of the pendulum, L is going to be the length of the pendulum arm, G is going to be the acceleration due to gravity. So, interesting to note, the pendulum's period is entirely independent of the mass. Doesn't matter how small or how large the bob is. If the length does not change. The period will always be the same. The other thing we have to watch for with the length, this is just a minor point, but like for example, if I have a pendulum, let me kind of sketch it here, my best possible pendulum. So we have a pendulum there, and then I kind of have this bob. The length of the pendulum is going to be taken from where it happens to be fixed, like the point it's pivoting around, to the center of the bob. So like this distance here, that's actually the length of the pendulum. It's not just the length of the string. You want to make sure that you get to the center of the bob itself. But like I said, that's a really small technical point. So yeah, this is your equation, works for all the pendulums. T equals 2 pi squared m over k is the general formula for the oscillators. This is a special case only for pendulums.